So we begin with the lecture on system of particles. Uh, First of all, let us consider a large number of particles. We will be first discussing the mechanics of the system of particles, and then we will impose constraints on these system of particles so that they behave like rigid bodies. So in this respect, we fix a frame 0, and we consider various mass points, and these mass points could have different masses. We have a mass mi for the ith particle, and its location from the origin of the frame 0 is given by the position vector ri with respect to 0. Let's consider another particle mj, and likewise its position vector is given by rj with respect to 0. And let's consider the center of mass to be located at the point C, and the location of the center of mass is given by this position vector r of C with respect to 0. The vector joining the center of mass to the ith particle is given by Ri with respect to C, and here you have Rj with respect to C. Let's assume that there is a force, an external force Fi acting on the ith particle. So we have the force on the particle I expressed in frame 0. You can see here that while we represent this graphically, we do not write the frame of expression because it has no meaning here. But when we write it in the matrix form as shown here, we have to we have to mention the frame of expression, because the components of this vector will depend upon the frame in which it is expressed. Here we have Fj, and then we have, let's consider a line connecting Mi with Mj, and also certain internal forces, the force that is acting on the mass point Mj and applied due to the particle Mi. So it's along the line joining Mi. So we write it as force on particle J due to particle I expressed in frame 0. Likewise, the internal force acting on the particle I due to the particle J will be equal and opposite to the force applied on the particle J due to the particle I, given by this relation. Next, we will come to the concept of the center of mass. You know that the center of mass is defined as the summation of Mi multiplied by Ri, that is the mass multiplied by its position vector. When you sum this for all the particles, and then this sum, this is the first moment of mass, this should be equal to summation Mi, as if all the mass is concentrated at the center of mass at this location C. Mass of the entire system, that is comprising all the mass points. So here, this is the definition of the center of mass. We can also write this because summation mi can be taken like this, and um, here you have Rc with respect to 0 expressed in frame 0. This is the position of the center of mass. Here all the mass is concentrated at the center of mass. Next you have all this mass can be written as if it is the mass of the whole system given by m, and here you have Rc. If we expand the left hand side, we can write this as summation mi Rc with respect to 0 plus Ri with respect to c. So we are just writing the position vector I with respect to 0, that is this position vector, as a summation of these two vectors. So you have the position of c with respect to 0 and the position of I with respect to c. So that's here. And that's equal to summation of, when you expand this, you get mi Rc with respect to 0 in the frame 0 plus summation mi Ri with respect to c in the frame 0. You have just expanded this, and that is equal to summation mi Rc with respect to 0 expressed in the frame 0. That is the right hand side. And here you see that, because if you see the previous step, you see here that you have a redundant term. So this becomes a redundant term, and so this has to be equal to 0. So by virtue of the definition, this is the result. See, summation of mi Ri with respect to c expressed in frame 0 is equal to 0. It means that if you take mass moments for the whole system about the center of mass, these moments will be equal to 0.